Welcome back to the deep dive. Today we're setting our focus on a topic that affects millions of children globally. And yeah, we're going to be laser focused on the science of how we might slow it down, myopia.
That's right. We're moving beyond just saying certain spectacle lenses work. We're diving into the biology, the mechanism sort of beneath the retina. Our source today is a really well-controlled 2-year clinical trial. It looked at the impact of these aspherical lenslets, the SAL and HAL designs, on a very specific tissue layer, the macular choroidal thickness, or CHT.
Okay, so let's frame the mission for you, our listener. We kind of know these lenses slow down axial elongation, right? That stretching of the eye that makes myopia worse. But why drill down into the thickness of this internal tissue? What's the goal there?
Well, the mission here is really about validation and maybe even more importantly, prediction. See, if we can show that how well these lenses work correlates strongly with a measurable biological change that happens pretty quickly, like these changes in CHT, then CHT could become a crucial short-term biomarker. It's a big deal. Imagine instead of waiting 2 full years to confirm the axial length is stabilized, maybe we could look at the choroid in just 6 months and get a good idea. Predict long-term success.
Okay, that makes sense. But before we jump into the trial results, we need to lay the groundwork. For anyone not steeped in eye anatomy, what exactly is the choroid and why is its thickness so important for eye growth?
The choroid. It's fascinating, really. It's this dense, highly vascular layer. Think of it like a complex network of blood vessels. It's sandwiched right between the retinal pigment epithelium, the RPE, and the outer white layer, the sclera. Functionally, well, it's a lifeline. It supplies oxygen, nutrients, all that essential stuff to the outer retina. But its critical role in myopia, the reason we're talking about it, is its influence on how the eye grows in response to vision, vision-guided eye growth.
Right, and this connection between the choroid and eye growth, it isn't straightforward, is it? Researchers usually talk about two main ideas, two pathways, maybe they even work together. Can you walk us through those hypotheses?
Absolutely. So the first idea is, well, pretty physical, mechanical, you could say. The theory is, if the choroid rapidly thickens, it physically pushes the retina just a tiny bit closer to the focal plane of the light entering the eye. This acts like an immediate buffer, sort of counteracting the optical signals that would normally tell the eye to elongate. It's a protective physical nudge.
Okay, that seems plausible for quick, short-term changes. But over the long haul, like years, that small mechanical push probably isn't the whole story, right? Which brings us to the second idea, the more complex one, the biochemical path.
Exactly. That's the signaling mechanism.
hmm
The thinking here is that a change in choroidal blood flow, perhaps triggered by the optical defocus these special lenses create, starts a whole cascade of events. This cascade involves signaling molecules, maybe growth factors, released probably from the retina that travel down to the sclera. And that signaling is what ultimately tells the sclera to remodel its extracellular matrix. And that's what physically changes how fast the eye is elongating over months and years.
Now, we did have some prior knowledge here. We knew from earlier studies the choroid is incredibly responsive. You mentioned before, simple plus lenses could make the CHT change in young adults in, 10 minutes?
Yeah, incredibly fast. But those changes were also known to be very transient, very reversible. You take away the plus lens, the defocus stimulus, and boom, the choroid pretty much snaps back to its baseline thickness.
Right. And that was the big question, wasn't it? The challenge for this long-term trial. If those short-term effects reverse so quickly, why would wearing these lenslet spectacles continuously make a lasting difference?
Precisely. The trial really needed to answer. Could these continuous low-level myopic defocus signals from the lenslets actually sustain that thickening, or at least stabilize the choroid, over 2 whole years? Could it override the natural thinning process we typically see as myopia progresses?
Okay, that sets the stage perfectly for the trial itself. We're talking a 2-year, double-masked, randomized clinical trial, RCT, that's the gold standard, isn't it, for proving something works. This one was done in China.
Absolutely. They recruited 170 children aged 8 to 13. All had mild to moderate myopia. The range was met at 0.75D to negative 4.75 diopters. And crucially, they were randomized into 3 groups, a 1-to-1-to-1 ratio, very balanced.
Group 1.
The control.
Essential. They got standard single vision lenses, SVL. This group basically shows us what happens normally, when myopia progresses without specific intervention.
Then you have the 2 intervention groups. These represent 2 different doses, if you will, of peripheral defocus. There's the SL group, slightly aspherical lenslets, and the HAL group, highly aspherical lenslets. The HAL design, well, it introduces a more powerful, more aggressive peripheral myopic defocus signal.
And the care they took with measurements. The rigor for checking choroidal thickness, it's really something else. CHT was measured every 6 months using swept source OCT, that's optical coherence tomography, state of the art. And to make sure the measurements were consistent, to remove variables, they insisted on taking readings only after cycloplegia.
Yes, that cycloplegia step is critical. They use 1% cyclotentalate. It temporarily paralyzes the eye's focusing muscle, the ciliary muscle. What that does is completely eliminate the influence of accommodation in the child trying to focus. It ensures that any CHT change they measured was genuinely down to the lens design or the underlying progression, not just momentary focusing effort.
Wow. But wait, the rigor didn't stop there, did it? They weren't just looking at the dead center of the macula. They used the ETDRS grid, which means they measured CHT across 9 different spots, subfoveal, parafoveal, parafoveal, like a detailed map of the response.
Exactly. And this next part, this is where the dedication really shows. The automated software on the OCT. It's good, but not always perfect at drawing the choroid boundaries. So they had 2 independent mask observers review the scans. If their measurements differed by more than 10 micrometers, which is incredibly tiny, less than a human hair's width head, they went in and manually corrected the boundary lines on the images. Both observers had to agree. That level of commitment to data integrity, ensuring 2 separate experts agree on these minute details, it just makes the final results so much more reliable.
That is just incredible dedication. Over 2 years for every participant, every visit.
Wow. Okay, so after all that meticulous work, let's get to the payoff, the results. What actually happened to the CHT over those 2 years in these 3 different groups? Well, the first thing that jumps out is just how dynamic the choroid is. CHT showed significant changes over time in all 3 groups. It confirms this layer isn't static, it's constantly remodeling.
Okay, let's start with the baseline. The SVL group, the controls, what did their choroids do? This tells us about normal myopia progression, right?
Right. And the picture was very consistent. The control group showed the largest, most continuous CHT decrease. Significant thinning.
Yeah.
This happened across all the measured regions over the full 2 years. And we're talking substantial amounts, roughly 12 to 20 micrometers of thinning, depending on the specific region. So this thinning, measured over time, it's clearly associated with the eye getting longer, with progressive axial elongation.
Okay, so basic myopia progression equals choroidal thinning. Got it. Now, what about these slightly aspherical lenslets, the SLO group? Did they manage to interrupt that thinning process?
They definitely did. They showed a clear protective effect. The rate of thinning was dramatically slowed down. Compared to the SVL controls, the CHT thinning was significantly reduced. But interestingly, they didn't completely stop it or reverse it long term. The SEL group actually saw a small increase in CHT in the first 6 months. You see that initial biological response kicking in. But after that, it started to decrease again, although, importantly, much, much less than in the control group.
Okay, so a moderate effect. Which brings us to the HAL group. Highly aspherical lenslets, the higher dose of defocus. This is where things got really interesting, I take it.
Oh, yes. This group essentially abolished the thinning trend, at least in the first year. It was quite striking. Their CHT actually increased significantly during that first year, by about 10 to 16 micrometers in some areas. So they successfully turned thinning into thickening. Now, they did experience some thinning again in the second year, similar to the SAL group, but starting from a thicker point. But crucially, the final measurement at 2 years for the HAL group was basically stable compared to where they started. It ranged from almost no change, like -0.30 micrometers, to an increase of nearly 9 micrometers in some regions.
Wow, okay, that paints a really clear picture then. The lenses with lenslets actively fought against that biological thinning tied to myopia progression. And the HAL design, the stronger one, had a clearly stronger effect. It looks like a dose-dependent response.
Absolutely. The biological response, the CHT change, it mirrored the clinical outcome beautifully. If you overlay the axial length data, how much the eye elongated, the pattern holds perfectly. SVL group had the fastest elongation, SAL was significantly slower, and HAL was the slowest of all.
Right, which brings us to maybe the most critical question for this whole idea of CHT as a biomarker. Was there a solid statistical link? Did the changes in thickness actually correlate with the changes in eye length?
Yes, and this is arguably the cornerstone finding of the study. There was a significant negative correlation. Changes in the subfoveal CHT, the thickness right at the center, were negatively correlated with changes in axial length elongation. And this was true across all 3 groups. The correlation coefficient ERS reached -0.53 in the HAL group.
Okay, for listeners who aren't statisticians, what does an R to omega 0.53 mean in practical terms here?
It means the two things tend to move in opposite directions. So as the choroid got thicker, the eye elongated less, it grew slower. Conversely, as the choroid thinned, the eye elongated more, it grew faster.
Yeah.
And an R value of neither 0.53 in a complex biological system like this, with all the variables in human children over 2 years, that's considered a strong, reliable correlation. It really strengthens the argument statistically that a thicker choroid acts as a kind of biological brake or buffer. It links CHT changes directly to the protective mechanism against axial elongation.
That really does make the biomarker argument quite compelling, rock solid, as you said. But let's circle back to that interesting dynamic in the HAL group. You said great increase for a year, but then it started thinning again in year 2. Even though they were still wearing the lenses, still getting that defocus signal, why would it revert?
Yeah, that's a fascinating observation. The authors themselves hypothesized this might be a sign of adaptation, neural adaptation possibly. The idea is if the eye is constantly bombarded with the same myopic defocus signal for 2 straight years, the retina might just gradually become less sensitive to it. It's possible that the strong, robust signal the lens initially provided wasn't quite as effective or novel in year 2.
Huh. So the retina essentially decides to, what, roll with the punches, figures out how to tune out the constant signal, letting the protective thickening ease off a bit. That's a really interesting glimpse into how adaptable the eye is. Ocular neuroplasticity. It suggests maybe just having the treatment in place isn't the whole story. The eye's response might change over time.
It definitely raises big questions for long-term treatment. Do treatments need adjusting over time?
Mhm.
Or does the eye just find a new, stable balance point? Which, thankfully, even with that second-year thinning, was still much, much better than the untreated SVL control group. Now, we should also talk about regional differences, because the choroid didn't respond the same way everywhere across the macula.
Right, they measured 9 regions. Did any particular area show a really distinct pattern?
Absolutely. The superior regions. That means the measurements taken above the fovea, towards the top of the eye. These areas stood out consistently across all 3 groups. In the SVL and SL groups, the superior choroid was either the most resistant to thinning, it thinned the least, or in the HAL group, it showed the most significant, most sustained increase in thickness.
That is strange, a real anomaly. Any idea why the top part of the choroid would behave so differently from the bottom or the sides?
Well, the authors are upfront about it. The reasons aren't really known. It's puzzling. Speculation includes maybe differences in the visual environment between the upper and lower visual fields, differences in underlying anatomy we don't fully appreciate, maybe even something like the localized effect of gravity, though that's really just guessing. But the finding itself is undeniable. The superior choroid seems to be the most responsive, or maybe the most protected region when it comes to these lens effects.
Interesting. Okay, before we wrap up with takeaways, we absolutely have to touch on that real-world factor that unexpectedly popped up. The findings around the 12 to 18-month mark, there was a sort of irregular blip in the data then.
Yes, that specific time frame, it coincided directly with a major period of the COVID-19 epidemic in China. The 18-month follow-up visit itself got slightly delayed for some kids. But more importantly, during that interval, the participants experienced about a month, on average, of intensive homeschooling, strict lockdown protocols.
Ah, right. Which we now know is like the perfect storm for driving myopia progression, isn't it? Loads of intense, close work, probably lots of screen time, and coupled with a big drop in time spent outdoors.
Exactly, and the data picked it up almost immediately. That specific 6-month interval saw the largest relative decrease in CHT across the groups. And consequently, it also saw the most significant jump in axial length elongation between any 2 consecutive visits in the study.
Wow. So even with the kids wearing these protective HAL and SL lenses, that intense environmental pressure from homeschooling actually caused a measurable temporary thinning of the choroid and a burst of eye growth.
It was essentially an unplanned natural experiment happening within their clinical trial. The authors think this was likely a transient CHT thinning. It probably recovered somewhat afterwards, but it powerfully demonstrated that immediate, strong link. The link between environmental factors like near work intensity, choroidal thickness changes, and myopia progression. It shows the biological pathway is still very much influenced by what the child is doing day to day.
Well, this has been an incredibly detailed look, really fascinating stuff about the biology behind these myopia control lenses. So just to summarize the core finding for you, the listener, these spherical lenslets, they actively intervene in the eye, they dose-dependently stabilize or even thicken the choroid, counteracting the thinning seen in normal myopia progression. And this directly validates CHT as a potentially useful short-term marker for how well the lenses are working, and confirms the choroid's role as a protective buffer.
Yeah, basically, if a clinician starts a child on these lenses and sees the choroid stabilizing or even thickening early on, say at 6 months, this study provides pretty strong statistical backing that the long-term outcome, in terms of slowing eye growth, is likely going to be favorable.
That makes the clinical relevance pretty immediate and powerful. And remember, as always, we've put a link to the actual study, effective spectacle lenses with aspherical lenslets on choroidal thickness in myopic children, right there in the description for you to check out yourself.
And please, if this deep dive gave you some new insights or food for thought, do take a second to leave us a 5-star rating and follow the show. We really do appreciate the feedback.
Okay, before we let you go today, let's just revisit that regional puzzle for a second. That finding that the superior choroid, the top part, had the most unique response. Least thinning in controls, most thickening in the HAL group. Not uniform at all.
Right. That's the kind of specific detail that keeps researchers thinking, keeps them designing the next study.
So here's a final provocative thought for you to mull over. Given that the superior choroid showed such a distinct response in this major trial, should clinical practice maybe evolve? Should we perhaps shift our monitoring focus from only measuring the subfoveal choroidal thickness, the very center, to paying closer attention to these regional measurements, especially looking at that superior area when we're trying to judge how effective myopia control is for an individual child?
That is a critical question.
Mhm.
Definitely something for future clinical protocols and research designs to consider very carefully.
We'll leave you with that thought. Thanks for joining us. We'll see you next time on The Deep Dive.